She finished her PhD in Universidade Federal do Rio de Janeiro, and now he moved here to IFT and ICTP-SAIFR. And she's going to talk on a very interesting subject, which is cosmology with gravitational waves. So let us see. Muito obrigado, Isabela.
Hello, everyone. Thanks for the invitation, for giving the colloquium. That's very nice. So I just started my first I started my first postdoc in April, and I'm working with Ricardo Sturani, and I will talk a bit about how we can do cosmology using gravitational waves. I hope that's not too boring for the students because they attended a very similar talk in the Colloquium recently, but let's see. So I will start discussing and giving the big picture of what is cosmology about and what is the standard model, and then what are gravitational waves. And finally, we go through different kinds of gravitational waves that we observe and how we can use them with different methods to learn more about the expansion of the universe and about cosmology in general. So first of all, cosmology is about studying the history of the universe in the larger scales. So it's about understanding how the universe came from something that was hot, dense, homogeneous and isotropic, not very funny, and expanded, and a lot of things happened, the physical point of view, and galaxies were formed, and something with complex structure was formed. Okay. The standard model of cosmology is the lambda-CDM model, which stands for lambda, the cosmological constant, and cold dark matter, which is a model with 6 parameters and based in the theory of general relativity. And this model tells us that today the universe, that overall the universe is composed of just a few things, and that today the distribution of these things is this one. So there are these two components, dark matter and dark energy, that make most of the universe today, and that we actually don't know much about them. So dark energy is the component that is responsible for the accelerated expansion that we observe in the larger scales of the universe, although gravity in the small scales is an attractive force. And dark matter is this excess of matter that we observe through its gravitational effect, but we don't know its composition. So although this model is very successful, it has these two big unknowns. And so this has been motivated people in the last couple of decades to propose alternative models to this one. And so the lambda-CDM model and also its extensions have been tested with different kinds of observations and independent kinds of observations. So I try to summarize here the main ones. So first, we look at the distribution of galaxies in the sky. So we look at distribution of the number of galaxies, also their shapes, and also sort of their distance, because we measure something that is very important for cosmology, which is the redshift. So the amount of Doppler effect that an object has with respect to us. Since the universe is expanding, the farther an object is from us, the faster it is moving away from us as well. So higher it is its redshift. Okay, so redshift and time and distance are very similar concepts. The second main probe of cosmology is the cosmic microwave background. So this first light that we can see in the universe, which is almost homogeneous and isotropic, but it's very small anisotropies in its temperature map and it's also in its polarization, reveal a lot about the early stages of the universe. And very importantly, third class of observables for cosmology are those objects that have some standard property, some universal property. And I will focus on this because that's where gravitational wave sources will enter, okay? So objects like pulsars, for instance, that we will talk a bit more about later, or supernovae, they have some quantity that is universal. So for instance, the supernovae are very, very important for cosmology because we can use them to measure distances. And that's a hard thing for cosmology to measure distances because things are very far away and space-time is curved. So there is not a single notion of distance in the curved space-time, and it's not very easy to measure it. Okay, but the peak of the intensity of a supernova explosion is proportional to its distance, to the square of this distance. So we can use these objects to measure distances. Okay, And if you can also measure the redshift of these objects, then you can show that the relation between these two observables, distance and redshift, it tracks the history of the expansion of the universe from the object to us. Okay, this h is the Hubble parameter. So it's tracking how much the universe expanded from there to until now. The Hubble parameter also contains information on the current expansion rate of the universe, the amount of matter of the universe today, the amount of dark energy, and so on. Okay. And with all these kinds of observations, until, let's say, 10, 15 years ago, everything seemed very right in the sense that independent observations agreed, and we could measure all these 6 parameters of the standard model. But there are these 2 big unknowns that are still not solved, okay? So a more modern, a more recent motivation for going beyond the standard model in cosmology are the tensions that for sure you might have heard. So notably the Hubble tension, so measurements made with more recent objects and measurements of the early universe physics, they point towards different values of the expansion rate of the universe today. Okay, and that was true for these two kinds of measurements, and today we have a bunch of other measurements that kind of continue to indicate this tension. And this is an unsolved problem in cosmology. So this was the beginning of the Planck satellite. Yes. So a Planck satellite it sees the cosmic microwave background, but there were already satellites before it that were measuring the cosmic microwave background. Yes. And so, sorry?
The last 4 blue, you said those are Planck. At least the first one you said was Planck, right?
These ones are different experiments, yes.
Okay, so they all confirm what Planck saw. Is that what you're saying?
Yeah, so Planck is here. So early universe physics. And shoes here is supernova and plus fades.
No, sorry, I'm looking at the first one.
Ah, sorry. These are just, so you have local distance lattice, so measurements of distance using supernova, phase, these kind of objects. And CMB measurements were different satellites that measured the CMB. So there was WMAP, for instance, and then there was
and where
Planck.
was Planck? That's what I'm asking.
Planck starts here.
Okay, and the other 3 are not Planck. That's all.
They are Planck because Planck took
Planck. Okay, so nothing
took
has
data
confirmed
several
Planck.
times.
So nothing has confirmed Planck yet.
Uh,
So the last 4 measurements are all the same experiment on the blue. Same group. That's what I was asking.
Yes, but yeah, I see what you mean. A lot of people look for systematics and these more experimental problems in the all sorts of experiments, but no one came up with something that could fix the tension until now. So, yeah. Yeah, it's true. Yeah, so this is a galaxy survey. This is a baryon acoustic oscillations that you see in the galaxy distribution. This is a Big Bang nucleosynthesis, but I don't know exactly what is this measurement. Yes, early universe. Yeah, yeah, so I would say most of the community thinks that is the tension between early universe physics and late time probes. But, yeah. And so there is really a lot of extensions of lambda CDM model. So they are older than the tensions, and they continue, and some gain forces because of the tensions, and some are already kind of discarded by several kinds of tests, not only with cosmology, but also with solar system tests and these kind of things. I wanted to show you this just to give an idea of the different ways that you can modify gravity, for instance. That is, let's say, the most popular way of doing extensions of lambda CDM is just to modify gravity. Okay. So I have been working with modified gravity. More specifically, I've worked with Horn-Desky theories. And these are basically the simplest modifications of gravity that you can have, because they introduce only a single extra degree of freedom, a scalar field. So now to say what happens with gravity, you have to say what happens with the metric and what happens with the scalar field. Okay. And they are the most general theories that do that by keeping the field equations second order, okay? So they are quite general as well. One feature of these theories is, for instance, that they introduce a sort of time-dependent effective Newton's constant in the cosmological constant. That is what I'm concerned with. So over cosmic times, there is some sort of Newton's constant that varies with time. And the good news is that the phenomenology of these theories in the cosmological context is well understood. So we know that, at least to describe linear perturbation theory in cosmology, all these family of models can only change the cosmological observables with 4 functions of time. So that's quite simple. Well, it's too complicated, but it's simpler than the general set. Okay. So, but now so they change the several kinds of cosmological observations and also the gravitational waves. And so but first let's understand a bit about gravitational waves. Okay. So gravitational waves are these very, very small distortions in the space-time that are generated by different kinds of things from the cosmological sources, like phase transitions in the early universe and so on, but very importantly by coalescing binary systems, which is what we observed so far. So basically, when they are emitted by these binary systems, the amplitude of the wave that we observe has these 3 phases. So an inspiral phase where the 2 bodies are slowly approaching each other, and then they merge, and then there is these final oscillations called ring down. The shape of this wave depends on several properties of this source. So the masses of each of the components of the binary, their spins, their position in the sky, and so on. Actually, the group of students of Ricardo, they worked basically on that, most of them, trying to model these waveforms, so solving the 2-body problem, basically, in different contexts. And while what I do is, so for what I do is more important to understand what is the distribution of these parameters. So how this population of binary systems is distributed across redshifts, what's the distribution of their masses, and so on. Because once we detect a bunch of these systems, then we can start to do statistics and understand about cosmology. And that will happen in the future, because we have detectors that are being planned, and they will see way more gravitational wave sources than the ones we have today. So today, what we have is LIGO, Virgo, and Kagra. So LIGO has gone through 3 observational runs and seen like 100 gravitational wave events. Now there is the 4th run going on. And yes, and there are these 2 called 3rd generation detectors, which are the Einstein telescope and the Cosmic Explorer, which are also interferometers like LIGO, and that are being proposed by Europe and the US. They will improve in sensitivity as compared to LIGO, if you look at here, and they will also see a broader range of frequencies. We just entered Einstein telescope. There was a Brazilian research unit created in the Einstein telescope that is being led by Ricardo, and there is also people in Rio de Janeiro and Vitória participating now. And yes, so that is very interesting. And there will be also LISA, which is being proposed, which is a space-based also interferometer. Okay, that is not in this figure, but its sensitivity curve will be here in the millihertz band. And there is also this different type of detection that is called pulsar timing arrays that we will talk a bit about later. That detects even slower gravitational waves, so in the nanohertz band. Okay.
Where's going to be built this Einstein telescope and Cosmic Explorer?
So from what I know, the Einstein telescope is not decided yet. But they are just deciding the site now. I think most likely in Italy, right? Yeah, in Europe.
In Europe. This ISA is what? I see.
Yeah.
Okay.
Yeah, and so it's very important to have these different detectors, not only to improve in sensitivity, because when you improve in sensitivity, you see farther away, so you see other objects, but also to have detectors in different frequency bands, because then you see different types of sources. You can see heavier objects, for instance, if you're looking at smaller frequencies, okay? So before understanding how we can actually do cosmology with these future observations, let's look a bit about what happens with gravitational waves in these beyond lambda CDM models. So in general relativity, these waves, they travel at the speed of light, and they evolve like radiation, which means that their amplitude falls with the distance to the source. This distance is basically the luminosity distance, that very same distance I showed earlier that you can measure using supernova. Okay, so this tracks the expansion of the universe, as I showed earlier. However, in alternative cosmologies, in general, I mean, here I'm not restricted to a particular model, but that's a general feature of modified gravity. This wave we propagate with a modified wave equation. So this is a wave equation in Fourier space, and here you have a friction term, okay? This friction term already exists in general relativity because that is the expansion of the universe. So the wave propagates, the universe expands, the wave is damped. However, when you are in modified gravity, you have a different friction rate here, this alpha m function. And also you can have a different speed of propagation, this alpha t function. You can even have other features, but I will concentrate on these two.
Say alternative cosmology. Do you really mean alternatives to general relativity?
Yes, I mean, it's because I'm looking at modified gravity theories in the context of cosmology.
But couldn't you have alternative cosmology without throwing away general relativity?
Well, you
You're saying
can...
general relativity implies that this lambda CDM?
No, not really, because there are considerations
Sorry, what
on
was the question? Sorry, I didn't
So
listen.
she's using the word alternative cosmology. I am interpreting it as alternative to general relativity.
Right, isn't it?
But general relativity doesn't imply lambda CDM. Why can't you?
Yes, you're right. By alternative cosmologies here, I mean cosmologies in modified gravity.
Okay, fine.
Because I'm not worried with what modified gravity does in a context that is not cosmology. So, yeah, but you're right. The general relativity does not imply lambda CDM because there are considerations on the matter, the constitution of the universe as well. And, well, so as I was saying, there are these two components that appear differently than in general relativity, which are changing the friction and the speed of these waves. The friction is affected by what I mentioned before, which is a kind of effective time-dependent Newton's constant. So we have the strength of gravity changing in large scales, and that also changes the amplitude of the gravitational wave.
When you say effective Newtonian constant, you mean that the usual Newtonian, the usual constant that appears in general relativity is multiplied by some function of this scalar field, or what?
Yes, in some context, yes. Yes.
Because in order to make this covariant, you cannot just add a arbitrary function of time for g, right? So I understand that what you have there is something that is a scalar, where g, you have some g that appears in general relativity times some function that's a scalar function of this scalar phi.
Field, yeah.
That's right?
Yes, that's right.
Okay.
But that is not the only modification that appears in these theories, okay? That is not just taking general relativity, and where there is g, you multiply by a function.
No, okay, I understand. Now, one extra question. This extra term in the Lagrangian is what? A scalar of curvature times phi, or what?
I will show the Lagrangian
Okay,
soon.
Thank
and we can, yeah. So, okay. So, in particular, and that is what I would like you to remember from this slide, is that this friction term, this excess of friction term, makes you attribute a different distance to the gravitational wave source when you measure its amplitude here, right? And so you define a different distance that is called the gravitational wave distance that is not anymore the same distance that you would measure with a supernovae, okay? It's a different distance that contains information on the expansion rate of the universe here inside this DL, but also on this time-dependent Newton's constant. Okay, so finally, let's try to get into the subject, which is how do we do cosmology with gravitational waves, how we constrain these beyond lambda CDM models with gravitational waves. So there are a bunch of models that have been proposed to do this. That is quite a new field, so there are people thinking about new things all the time. And I will focus on these three types of observations and tell you a bit about it. So first I will discuss the stochastic background. Then the dark standard sirens, which are those events that you can see, but you can only see the gravitational wave. And then we talk about the bright standard sirens, which are multi-messenger events, which is what I worked mostly with until now. So the stochastic background. So a stochastic gravitational wave background can be generated by different things, but the one that is generated by astrophysical sources is basically a net signal of gravitational waves of all these sources, of all these binaries that are too weak to be identified individually. Okay, but their net effect can be detected, and actually it was detected just in June, if I'm not mistaken. Yes, hopefully. No, it was detected. It was detected. Yeah, it was 5 sigma. Yeah, I think there is a big evidence that it is the stochastic background, but we just don't know. Is the stochastic background formed by what, emitted by what? I think that's the more unknown, but we get into it. So, yeah, as I was saying, this is a very, very weak signal because you cannot identify any of these sources individually. But this is hidden in the noise of the detectors, okay? If you have a bunch of interferometers detecting gravitational waves, this stochastic background will be there, hidden in the noise, such that if you do the correlation between the signals that the two detectors are seeing, this correlation will pop up, okay, pop out. So you will see some signature of this stochastic background. And so basically the main observable of this background is the correlation between the signals from two detectors. And you can show that this correlation is directly related to the energy density of gravitational waves, such that you can model this energy density depending on the kind of sources that you have. You can have a lot of information on the astrophysics of these binary systems and also on cosmology. That's something we cannot access yet. Okay. I've worked a bit on that, on stochastic backgrounds with people in UFRJ. And basically what we are interested in was to understand whether, when we are in a Horn-Deskey theory, in a modified gravity scenario, even if these theories, they recover general relativity in the early universe, but after that, they do not. What happens with this background while it propagates throughout large distances? Okay, and we found out that, curiously, the energy density of this background is not changed. Okay, and however, the observable that we expect to see will change. Okay, so this correlation between signals of two different detectors, it will carry an overall factor here that depends on this time-dependent Newton's constant. Okay, we don't know if if we can measure this, but that is the effect. And as I was saying, the stochastic background was detected very recently. And it was detected with a totally different kind of detection method, which are these pulsar timing arrays. So how does it work? So these pulsars, they are neutron stars that have these big flares emitting particles because of strong magnetic fields. And they rotate in a very regular manner, okay? And we track these pulsars for years, and we know how their period changes, okay? And if there was a gravitational wave background in the middle, in between the pulsar and us, what will happen is that this gravitational wave will distort space-time. And so it will affect the periods of these pulsars, okay, through time dilation. And so this is a very, very small effect that we cannot see by just looking at a single pulsar, but we can see by looking at the correlations of the excess of timing of period of different pulsars, okay, if we have enough pulsars. And so that's the technique. So basically, if you do this computation, you can show that the correlation between the timing residuals of all the pulsars that are separated through a fixed angle in the sky is this function here, is this dashed curve, which is called the Helling-Downs curve. And these error bars here, these are the detection. So yeah, doesn't seem very good with this picture. Ah, okay, thank you. But there is a Bayesian evidence also to believe that this is a stochastic background. So for instance, they compared if this could be generated by just Gaussian noise in the measurements of the periods of the pulsars. And with respect to this, the Bayes factor is like 10 to the 14, is very high. So they did several tests that kind of indicate that this is a stochastic background of gravitational waves. Sorry?
How do you know the effect from the pulses came from a gravitational wave?
Because if it comes from gravitational waves, it has this particular behavior with the angles.
And only gravitational waves could do
Well,
that. Is that the idea?
As I was saying, they tested with different scenarios, so they can assume you have Gaussian noise it's just Gaussian noise, how the noise would be correlated, if it's something else.
Sorry, I'm confused. Does this have anything to do with detection of gravitational waves or not?
Yeah.
So they're not, but are they detecting it's not like LIGO where they detect the gravity.
No, it's not a direct detection like LIGO. I think
it's indirect.
That's what you mean. Yeah, it's through its effect on the time dilation. Okay. So
the pulsar signal is like the laser of LIGO.
Yeah.
So the pulsar signal is the laser, and you see the mismatch in the time of arrival of the pulsars. So if it's a quadrupolar perturbation that does that, then you should see this correlation. Basically, that goes to 1/2 when the two pulsars are in the same position, goes to 0.2 when the two pulsars are in the opposite point, it goes negative when the two pulsars are at 90 degrees. This is a fixed prediction for a light beam that is arriving from all of these possible directions when a quadrupolar perturbation is passing by.
Yeah.
So basically, the quadrupolar perturbation is the gravitational wave, and the beam of the pulsar is what the laser is for LIGO.
Okay, so it's detecting the laser. It's detecting the light. Is that what you're saying?
It's detecting of light, like in
Like
LIGO,
in LIGO,
you detect
yes.
light.
Okay.
In LIGO, what you see is the effect of the time of the stretching of the arms, right, through
Yes.
the interferometry. So that's similar also.
LIGO is not able to detect a signal with the frequency that PTA is able to.
Yeah, so what they detected was a signal compatible with this amplitude, but in the nanohertz band, which is far away from LIGO band. Okay. And they looked for different kinds of things, like if this could be generated by a single supermassive binary black hole, these kind of things. They looked for anisotropies, they didn't find anything yet. So they couldn't really say what is generating this background, but we expect that it should be there, because we have seen gravitational waves from binary black holes, so there should be a stochastic background. Okay. And so the most standard assumption is that it is formed by supermassive black hole binaries, which are these black holes with millions and billions of solar masses that are in the center of galaxies. So, yeah, that's it. So, okay, so those were signals that we cannot see individually. But what happens when you can see the binary black holes individually, but we can only detect the gravitational wave that they emit? So we don't see anything else, don't see any photons, okay, in particular. So these are called the dark sirens. And the question here is whether we can do cosmology with them. So when you see a binary black hole, not with the eyes, but with a gravitational wave detector, you can infer several properties of this binary, right? The masses and so on. And most importantly for cosmology, the distance. And you can also have a poor information on where it's located in the sky. The question is, the important thing is, we don't measure its redshift, okay? Because you don't have any photons to measure redshift. And so you cannot just compare distance with redshift and measure the expansion rate of the universe with these kind of observations. So how do you solve this problem? So what people have been thinking is that we can use a galaxy catalogs. So we have galaxy catalogs. We know a lot of galaxies. And we can ask ourselves which galaxy is hosting this binary system. And if we get to know this, then we can just get the redshift of the galaxy. The problem is that you have a very bad uncertainty in the sky position. So in practice, there are lots of galaxies in that region in the sky that could be the true host. So what you need to do is to first to have a lot of binary systems to accumulate statistics, and then to have some idea of how likely is that such some galaxy is the true host of that binary. So you can do different assumptions here. You can, for instance, consider the luminosity of the galaxy. Maybe it has more stars, maybe it has more binaries, and so on. And this method, what this gives you? This gives you a very broad and like multimodal distribution for the redshift of a single binary. And yeah, that's because of the uncertainty in the sky position. And here I'm showing you on the right this figure of some of the LIGO observations, such that you have an idea of what is a bad resolution. So it's really a huge portion of the sky. When you have more than one detector operating, which is the case of these two events, which were seen by Virgo as well, then you kind of triangulate and you reduce a lot these uncertainties. Okay. Another problem is that is the incompleteness of the galaxy catalogs, and that is something we're interested in studying. So the galaxy catalogs we have there, they don't have all the galaxies up to a certain distance. Okay. So what if the true host of that binary system is not in my catalog? Maybe I will bias my results. And so to kind of go around this problem, you can also consider what is called the empty catalog case, which is basically to say that there is already a prior probability of the redshift of the events, because you know how the population of black holes is distributed, you know its history, okay? So you have to consider, for instance, that there are more binaries if you're looking at a larger volume in the sky, and it also depends on the expansion, on the star formation rate and the time that a binary system takes to coalesce and these things. So that's a lot of modeling, and that's one problem of this method, okay? But it works. So I would like to show you just these two plots so that you have an idea. So here on the left, you have a bunch of constraints on the Hubble constant from individual sources, dark sirens. There is no information at all, you can see. But when you put them together, you do end up with some reasonable constraint. And here on the right, you can see the results of all the detections that were made so far, up to the end of the third observation run of LIGO. So here in blue, you see the result of dark sirens. It's very broad. Okay, these are 100 events. But with third generation detectors, you expect to see even hundreds of thousands of events. So that will improve. And here, this dashed line is the result from a single bright siren that we will discuss next. And here in black is their combination, okay? And these two are those two older measurements of H0 with supernovae and with CMB that are in tension. Okay, so let's discuss now about the bright standard sirens. Sorry, there is a question. With the binary. You know the distance. Because you don't know the distance of galaxies. You know their redshift. But yeah, exactly. So you're comparing these two distances, if you want, redshift and gravitational wave distance. So bright sirens. So bright sirens are these very special type of gravitational wave events that also emit other messengers, so photons most importantly. There was just one bright siren that was detected so far, which was this GW170817 in 2017. It was seen by LIGO and also by several other telescopes. For instance, it was detected as gamma ray bursts and also the kilonova. And that brought a lot of information, especially because this event was very close to us, was in 40 megaparsec from us. And so there are different things that you can do studying these objects. There are different methods. First of all, there is the time delay. So you can compare the arrival times of the two messengers, of the photons and the gravitons, and this gives you a direct measurement of the propagation speed of the gravitational wave. Okay, and that was done, in fact. So with this just one event, we could measure that the speed, we could see that the speed of propagation is basically the speed of light with this precision, 10 to the minus 15. So that was quite a strong bound. Okay, that had been predicted before by these people. And that was actually very, very important for modified gravity, because there were dramatic consequences to modified gravity, because there are lots of theories that predict a different speed of propagation, as I said before. And so for someone who asked, this is the Lagrangian of the Horn-Desky theories. Don't mind the details, just to give you an idea. And so you have here the scalar field phi, this kinetic energy x. And basically, the fact that the gravitational waves should propagate with the speed of light kind of disfavored all this contribution here, L5, and also this contribution here. Okay? So that is very dramatic. If you take into consideration that this Lagrangian is defined with these four functions, G2, G3, G4, and G5, for free functions, and you killed all the G5, you killed also this dependence on the G4, so that's a lot. So phi is this scalar field that is responsible for, is dark energy, if you want. Okay, so it's this extra degree of freedom that should make the universe expand at late times, expands accelerated. Yes, something else, yeah. It's another field. Positive energy, what do you mean?
If you take the Lagrangian and ask them if you want the energy to be positive.
Which energy?
The energy. The
energy density of the field.
So, so I see things like box phi squared, things like that. Those are usually sick theories, right? In field theory, you would never consider a box phi squared theory. At least I would never consider a box phi squared theory.
Well, I'm not sure if I understand the question.
I look at L4,
so that is the kinetic energy of the field.
Yeah, but if you do field theory, normally those theories are sick, right?
But I see what you mean. These theories, they are not all healthy. They have to respect some conditions that are called stability conditions, so that you prevent that there is a negative energy, and there is also negative speed of sound, for instance, and things like that.
No, what I'm saying, Nathan, you see, it multiplies the G4x, which has some constraints for the positive energy condition, but you just looking at it, I don't see how you can tell that that's sick. Until you tell me what is G4, how can you tell it?
Okay, yeah, but I could say the opposite. Until you show me that that thing is consistent, I would think that it's not.
Okay, but
so you would have to tell me what G4x is in order for that to be consistent, and maybe there's no solutions. I don't know, I would have thought that...
No, but there is, these theories have been around for 30 years. People have checked it.
This was written in 72, I think.
These are higher order theories, right? These are higher order theories. So if you assume, that's the question. If you assume this theory as a Cauchy problem, if you assume this as a Cauchy problem, in order to evolve it, you have to give not only the first derivative of the field, but second or higher derivatives.
These are second order theories.
Second order theories?
You can show that the equation of the field equations, they are second order in the scalar field and in the metric.
That's actually the constraint on this field.
Yeah.
This is the most general second order.
Yeah. But yeah, these functions, I mean, they are free functions, but they cannot be that arbitrary. They have to respect some inequalities, if you want. Okay, but that's it. And so the thing is that gravitational waves have been shown that it is very strong observation. These are very strong observations to constrain this modified gravity scenario, okay? Especially when you have hundreds of these kind of bright sirens. With LIGO, we detected one, but we expect to have hundreds. We don't know for sure how many, but with third generation. So that was a measurement of the time delay. So a second type of test that you can do with bright sirens, and that's what I worked more with, is this distance redshift relation. Okay, so you measure, you see photons, you see gravitons, you measure both redshift and distance. So you compare these two, and you measure the expansion rate of the universe. That's very simple. The thing is that this distance in this context is now modified, as I showed to you. There is the expansion of the universe here, but there is also a contribution from this effective Newton's constant that appears, is in this function psi. And so there are different ways in which dark energy is modifying this function. Okay, you have to be able to constrain all these together. That's the challenge, the number of parameters. I have done some forecasts for the Einstein telescope and draw some conclusions out of it. So for example, for the theories called f of r theories, maybe you've heard of, they are contained in these Horn-Deskey theories, okay? They are also a family of theories that depend on this function f of the Ricci scalar. You can show that whenever you fix the cosmological parameters, so the Hubble constant, the amount of matter in the universe today, these kind of parameters, then you can put percent level constraints in these theories without specifying the specific theory, okay, without specifying the function f of r. Okay, so that's something you can do. However, that's not very good when you free the cosmological parameters. Because what we see is that this kind of test, in this kind of test, you have large degeneracies between the parameters, okay? So you cannot distinguish very much a scenario in which you have just a bit more matter in the universe or a bit of modified gravity. It's a bit degenerate, okay? However, that's still, this kind of test is still useful when you combine it with other cosmological probes that break these degeneracies. So for instance, here I'm showing on the left a combination of the CMB constraints of Planck, which is these blue bananas, combined with this distance redshift relation with future bright sirens with the Einstein telescope. So you have some quite good reduction on the measurement of H0, for instance, which is this parameter. And you also have some improvement in the measurement of this parameter here that is tracking the modification of gravity. It's tracking the time-dependent Newton's constant. Okay. We also investigated that there are particular observables of the large-scale structure of the universe that are affected by the exact same features of modified gravity that the gravitational waves are. And that is very interesting, because then you can combine these two types of observations and measure specific features of modified gravity without having to say a lot about what the model is. So these are more model-independent constraints that you can put. And that is the case for the observable called gravitational slip. So in modified gravity, there are two gravitational potentials in general, in large scales. One that governs how light is bended through wick lensing, and one that tells us how much matter clusters. So one for photons, one for massive particles. And this observable called gravitational slip, it measures the difference between these two potentials. So it's a direct observable to track modifications of gravity. It's very standard. So you can, and we investigated the fact that the same two functions, the gravitational speed and the gravitational wave friction, they also generate this gravitational slip. They are the exact functions that generate gravitational slip. And so, for instance, we looked at, okay, so which type of observation will give us better constraints, better measurements of these effective Newton's constant and things like that. That is something we investigated. And they are similar. Okay. So the last thing I wanted to mention is these third types of methods that you can do with bright sirens that based in the fact that gravitational waves are tracers of the total matter field in the universe. So they are biased traces, like the galaxies are, of the underlying dark matter and the total matter, okay? And so with bright sirens, there is something very special, which is you can measure both distance and redshift, and that gives you information on the peculiar motions of their host galaxies. Why? Because if you measure the redshift and you measure the distance, you know which part of the redshift is due to just the cosmological redshift because of the expansion of the universe, and the excess of redshift that you eventually measure is because there is some peculiar motion, some motion of the galaxy with respect to the Hubble flow. And so these bright sirens, they can be used to measure what is called the velocity field of the galaxies, okay? And also the density field of the galaxies, as I said. So you can construct these different kinds of fields, the density field of the galaxies, the density field of the gravitational wave sources, and the velocity field of the galaxies. And the correlations between these fields is sensitive to several things in cosmology. So very importantly, it is sensitive to the growth of structures. Okay, the growth of structures is a function that tells us how small perturbations in the large scales grow with cosmic time. Okay, so it's an observable of the perturbation, of the cosmological perturbations. So it has been shown, and there are people in Brazil working on that, that these observable can be measured with using bright sirens. Of course, for all these methods that we have been discussing, we can ask whether it's better to use gravitational waves or supernovae, right? We have more supernovae than gravitational waves, okay? And we will have also in the future with LSST more supernovae than gravitational waves. However, there is some feature of gravitational waves that is different from supernovae, which is the fact that you don't measure direct distances with supernovae, because their intensity peak, the peak of the intensity is proportional to the distance, okay? So you need to calibrate this proportionality constant, and you need other objects to do that, like Cepheids. And so this puts some lower limit in the errors that you always get with the distances with supernovae. And this does not exist with gravitational waves. You can have events that you measure very, very precisely the distance, okay? And there is no calibration involved, which also kind of eliminates further systematic problems that you might have. So that's, this should be complementary objects. And so the conclusions are, so the overall conclusions that I would like you to remember is that there is a lot of cosmology that can be done with gravitational waves. There are different methods that are being created. We are working on that, and a lot of people working on that. Mainly, they are distance indicators, so they are objects that you can use to measure distance. They are also tracers of the matter fields, and these are the two qualities that really are important for cosmology. And in the context of beyond lambda CDM models, they track specific features of these models. So they track two functions, basically. One was already measured, that is the speed. So now they track one function of these models, that is that time-dependent Newton's constant. That's very important, because then you don't have to specify what happens with these models. You don't have to pick a specific model to study what happens with gravitational waves. You can do it with large classes of models. And their combination with other probes is very interesting to break the generacies, okay? So my interests now are exactly this, to explore combinations of gravitational wave detections with other probes. So I'm working on the combinations with supernovae in the context of modified gravity, also with cross correlations with galaxies. And I would like to build more model-independent tests of gravity using these kind of events. So especially with the dark sirens. Okay, as we were discussing before, for the dark sirens, you have to kind of take a distribution of redshifts from our galaxy catalog, things like that. But for the method that is already there in the literature, you have to specify a model. You have to say it's lambda CDM, or is this model or that model. I would like to investigate more model-independent approaches. And that's it. Thank you.
Okay, good. Thank you very much. Questions? Oi?
Sorry, what's the limit that you get for the time dependence of Newton's constant from these measurements? Can you tell us?
From these measurements,
Well, the things that have been measured up to now using gravity
Yeah.
waves or supernova, how well do we know? I mean,
Okay.
what's the limit on the
so,
change?
so for instance, when you fix the cosmological parameters, that is a percent level measurement, okay? So 1%, 2%.
So what does that
uh,
mean? From the beginning of the universe until now, it's 1% change? Is that what you mean?
It's more from the source to now. Yes.
Okay, and the
so
source is...
sources are typically at redshift 1, let's say.
Okay,
So in the
thanks.
late universe until now. But there are local tests of gravity also that restrict this function, okay? But let's say they measure the variation of the Newton's constant locally. So I'm not sure things are the same.
Okay,
Okay.
thanks.
Actually, I have a question. So what's your opinion about what's our chance of measuring some gravitational waves coming from inflation with the PTA, with PTA?
With PTA, I think inflation is one of the possibilities of this signal that they detected, but they cannot really rule out any model. So we don't know yet, but I think we will detect. I think we will detect also in the cosmic microwave background. So because
With the
that is an effect
polarization.
also in the B modes of the cosmic microwave background.
But do you think this is I mean, a real possibility? Can we really expect? I am almost 60 years old, so I'm really interested about how long that's going to take.
Yeah, so I cannot answer this
Oh,
question. I don't know.
My question is, in fact, related to what Jorge just asked. So that form you expect for the correlations between the pulsars, the dashed black line that you had in your plot,
Sorry.
that is independent of the source for so if this is coming from binaries or from inflation, it is exactly the same shape, or?
I think there are just a few assumptions here, like it's a stochastic background, it's isotropic, it's unpolarized, if I'm not mistaken. There are the basic assumptions that you do to arrive in this function, in this curve. But
So
what
white noise is in there, like it is independent of frequency, or is just that
No.
for that particular frequency?
yeah,
that you-
so that's the thing. If you can detect this background in different frequencies, then you can reconstruct the spectral shape of the background, and that gives you information on.
Oh,
which
okay.
j-
So
what
the
was
problem here is that you're looking at only at one
specific
frequency.
frequency,
Yeah,
very
okay.
narrow band, very
Okay.
narrow frequency band. Yeah,
Okay.
exactly.
So if we manage to start looking at these using the detectors, then we'll be able to, I don't know, this Einstein future. Ever, okay.
Yeah.
Okay.
But then it's the other type of detection, is through correlating noises. With interferometers,
Trying to look at the stochastic background by correlating.
yeah.
No, I understand that. But if you look, this observation at this frequency, and observe also the stochastic background and a completely different frequency, then you're getting some information, if I understood her answer, about the source. right? If
Yeah.
the source is contributing to all these frequencies,
I think you need to look at a band of frequencies to be able to see like the shape of this function. Yeah.
yeah, okay, yeah.
Sorry, I'm losing the physics. What's determining the frequency of 10 to minus 9 hertz? I'm sorry. What's
Yeah.
the physics that determines this? I'm losing the physics. So
It's the time of observation, as Ricardo was
time of
saying.
observation.
Yeah.
But so in order to move from something else, we have to see, say, billion of years because. Yeah, I know. I know. Okay, but if we keep looking for 20 years, how large is the band we are going to be able to probe? Okay.
So my question was basically what George just said. What? Oh, sorry. My question was basically what George just asked, but also I was thinking about this for 20 years, if we gather the information and this band of frequency that we get, can we actually probe the frequency distribution? And like, for instance, say it's a massive
Yeah, so
black hole
for sure you measure a
binary
bit
or-
more frequencies, but I don't know, I haven't seen their forecasts for
Okay,
this, so
okay.
I don't know how well this will improve the constraints on the models in the end. I don't know.
Okay.
I wouldn't expect that they were able to say it's this, but maybe they can rule out something.
Sorry, this Einstein telescope is being funded by, when I said ESA is the European space, no.
Einstein telescope is on the ground, so space
Yeah.
is not involved.
Okay, but so who is putting money in this?
The states that are building it, I mean, it's not decided in which share each state is
Okay,
contributing.
so it's still in the
But-
beginning.
Yes.
Okay. Other questions before cakes? No? So Isabella, thank you very much for
Thank you.
your very nice colloquium.
Thank you.